As we go forward in the simulation, Eugene is bouncing off the wall and he's not quite pushing through. And so in order to adjust this, we'll need to change the mass of Eugene. In other words, how heavy he is so that he'll pass through the wall successfully. And mass of an object is calculated in one of two ways. So if we go to Eugene right here, you'll notice that the mass is grayed out and instead we have density. The way this works is that what the bullet solver will do is it'll first of all calculate the volume of each piece. So it'll look at how much volume exists with Eugene. The bigger he is, obviously the more volume there is, and that gets multiplied times this number, density. Once that product has been made, that is what mass is, and that affects how light or heavy the object behaves. So density is great when you have different pieces and you want those different pieces to have different weights. As we saw when we crushed Eugene and we had the pieces floating up in the Y direction earlier in the course. In this case though, I want to show you the other way of doing this. Let's say that I want to just have a mass that I specify. I don't want this based on density. Well, if I uncheck this compute mass, this will allow us to manually set what that value is for Eugene. So I can turn it up here, or you can also source that in by doing something like this. You could say f at mass is equal to any kind of number. So let's try 100,000 and see what that does. So at 100,000 we have about the same results. Let's go ahead and add a couple more zeros to that. Let's try that. Maybe 10 million. See what happens there. And with that change, now we are beginning to break through successfully. So real quickly, I want to demonstrate what bounce does. If we hover over the tooltip, this gives us a clue into how this works. It says that bounce is the elasticity of the object. If two objects of bounce 1 collide, they will rebound without losing energy. If two objects of bounce 0 collide, they will come to a standstill. So the way to think about this is preserving the energy, right? So if we say that the bounce is 1 on the ground and the RBD packed object also has a bounce of 1, that means that no energy is being lost when the sphere goes to bounce and it ends up right where it started as it went down. In practice, what this means is that if you need something to be bouncier, you turn it up closer to 1, and if you need less bounce, then you turn that value down. So if I turn this down on the sphere, and let's say on the ground plane, both of those things will influence the bounciness. It's really pretty self-explanatory, so I'm not going to spend any more time on that. Also with friction, friction is, well, what it sounds like. It's how much an object will slow down as it's sliding on a surface. So if you turn that up, you get more friction. And last but not least, let's talk about some of these constraints and how to set their strengths up in a way that makes sense for the mass that Eugene currently has. So back here we specified mass, and I believe right now that's at about 10 million. So let's copy this 10 million, and what I found is that when it comes to these constraint strengths, you want to figure out the mass of the thing that's hitting it and start there with the strength. So if we start at 10 million, most of these constraints are not going to break very much. And so just to give an example of that, I'm going to cache this out and we'll see what that looks like. So as you can see, we only have a couple of rocks that come loose. Let's try doing about half that though. So go to the ground constraints and set this to 5 million instead of 10. Cache that out and let's see what that does. All right, so we're starting to get somewhere. That's knocking a few more pieces loose, but let's keep going with this and go even half of this. So we'll do 2,500,000 and cache that out. With a glue strength of about 1 million, we're just starting to break through the wall. And so the idea here is you want to find that value that just allows you to break through the object. And then once you're about at that correct value, then you start fine-tuning the glue propagation rate, and you can kind of go from there. So we know that 1,000,000 is what it takes to get him through the wall. What happens when we bring this down a little bit more? So maybe let's try 500,000 as an example. So 500,000. And if we change our half-life, this is going to change the way in which force will propagate through all the constraints. So let me explain what this is visually. Let's say that Eugene hits the constraints right about here. What's going to happen is that the force of that impact is going to travel through the other constraints. So it's going to go in all sorts of different directions and spread outwards. Now, as that force spreads outwards, let's say that we start at a value of 10 and we go over here. Let's say by the time the force is over here, that value is 5, right? It's going down over time. And this half-life is referring to how quickly that value reduces over time. So a value of 0.1 is saying that it'll take 1/10 of a second for us to reach half of whatever value is happening on the constraint. So again, we're at, let's say, a value of 10 for easy math. It's going over here. And let's say that by the time it reaches this area of the constraint network, it's been 1/10 of a second. Well, we said half-life is 0.1, so that means that now 10 gets turned into 5. And then that is how we control how quickly force gets spread across the constraints over time. So let's actually try 750,000. Let's get somewhat close to that 1,000,000 that we had before. Let's also highlight both of these constraints so that we're doing the same value. So 750,000. And then with the half-life, let's set this to a value of 0.5. So a value of 0.5 means that it'll take half a second for that force to be reduced or turned into half the value. So in other words, it's going to increase the amount of force that propagates through all the constraints over time. Or it'll basically prevent that value from decaying because it takes a full half second to reach, half of the original value. Okay, so in doing that, let's cache this out and see what happens. So now we have some of these constraints breaking over time. It's a little bit more subtle, but you'll notice it in the areas that break after Eugene has left the top portion of the wall. So some of these stones that just fell off, those are perhaps good examples of how something propagates over time and allows them to break off. Let's go ahead and actually turn down our strength here, though, so that we can see a more pronounced effect. So let's try 500,000. And after adjusting the glue strength to about 200,000 and the half-life to 1 second, we end up with this. And I really like how this result turned out. And so the last thing I want to do is I want to have Eugene stick his landing. In other words, I don't want him to fall forward once he gets right about there. So to do that, what I found, it's actually took me a little while, but I came up with a really fun trick where all you need to do is keyframe the drag that happens on Eugene. So if we just take these two drag nodes, which have been keyframed ahead of time, at least these are, what I keyframed ahead of time. We have the regular drag on 70, that's 0.075. And then on the next frame, on frame 71, I just crank that all the way up to 0.75. On the drag spin, I do a similar thing from 0.1 to 1.5. And so after doing that and caching this out, let's see what happens. All right, and this is pretty sweet. Eugene, he's cruising through the top here. He's doing the front flip. He sticks the landing, and it all looks pretty cool. Now, depending on your scene, you'll have to adjust this because There's many different factors that go into how he lands. You know, if you have a different fracturing going on, or if you have all sorts of different things, you might have to adjust for the situation. But this is the main idea that we're going for. And in the next video, let's talk about the time warp node and mess around with the playback speed of what we have right here.